Okay, so welcome back to another video. Here today we have the limit as n approaches infinity of n times the definite integral from 0 to 1 of 2x divided by 1 plus x to the power n dx. So we have a combination of two well-known topics taught in an elementary calculus course. We have a limit and of course an integral. So this is maybe looks a little complex here, just dealing with the fact that if you're looking specifically for the integral, it may look difficult to see that using your standard calculus techniques might not work, but it's actually possible. It actually does work, as a matter of fact, and you'll see why. Specifically, if you try to use u-substitution, that's definitely going to work, but it's not going to work in the sense of how you're taught, because once we get to that, eventually when we get to that, it's gonna we're gonna work things a little bit differently. So eventually, using that whole idea with u-substitution, then eventually we can actually write this in a way that if we simplify and factor some things out, we can actually write this in terms of geometric series, utilize that, then of course we have to take the account of the limit as well. So yeah, and everything from else will just flow on nice, basically. So nothing else I want to add to that, so why don't we just jump in. So suppose we're gonna evaluate this definite integral first. So let me just call this I'll just call this a sub n, since here we have recursive for n approaches infinity. So I'll say that this is the definite integral that we're trying to evaluate, 2x, and then divided by 1 plus x to the power n dx. Then let's perform a u-sub. So u is equal to, so we'll set that to the inside quantity, so 2x divided by 1 plus x. You can try to differentiate both sides to get du, but you also have dx. And that's actually going to make things a little bit difficult, since we want to substitute things back for, well, we are substituting back for dx, but the problem is that, of course, things are just going to get a lot, messy, and it's going to get a little bit more repetitive to that point. So why don't we manipulate our u so that now this time we're actually dealing with just x. So if you'll notice that if you actually fix all this up, we're going to get that x is actually just equal to u then divided by 2 minus u. And then you can literally see this for yourself once you actually just perform the necessary algebra. Then if we do the differentiation both sides, so we're going to get that dx is actually just equal to, so here I have so 1 divided by 2 times 1 minus u divided by 2 square du. So of course you have to perform the quotient rule, but afterwards you can actually just do a little bit of factoring, and that's how we get the denominator you see right there. It may not look as common, but that's the appropriate way to do this, because eventually once we get to future steps, then you'll see how things will come into play. When we plug this back in dx, then plug in u, so now we have that, so we have our new integral, but don't forget, if you have to change the bounds, but that's not really an issue, since it's going to stay the same once you plug everything for x in terms of u. So that's fine. So now our integral still stays the same from 0 to 1. So now we have that u to the power n, just plug that back in. Then it's divided by 2, and then to the power 1 minus u divided by 2 square du. Now if you actually keep going a little further, so what I can do is I can factor out the 2 outside, so that's really a 1/2. Then we still have our integral 0 to 1 u to the power n, then divided by, so I'm gonna actually expand this out further, not exactly expand it out, but more like expand the product. So in other words, I'll just write it as the way it's look like as a binomial factor. So 1 minus u divided by 2, and then just write that again a second time, and then du. Okay, then you'll notice that now I said that we can actually apply the geometric series. It makes sense to do so, since we're integrating between 0 to 1, and our common ratio would have to be from 0 to 1 over here. Then we'll just substitute that back in, so now we have that the new integral is 1/2, then 0 to 1 of, so it's actually going to be u to the n, then multiply with the products of the geometric series. So I'll label these indices a little bit differently. So this is infinity, I'll call this k, then this is from u divided by 2 to the power k, then multiply with the same geometric series again, but let me label this as our indices as m is equal to 0, of u divided by 2 to the power m, and then this will be du. what you can see is that not only geometric series for specifically in this, they're absolutely convergent, so we can actually switch the signs. So I can actually move both the sum and the integral symbol, just flip that around. But also, if you distribute with the exponents for both the denominator, they're also constant, so that can go also outside as well. When you distribute with the variables for u, and then there's also u to the n, so we can use the rules of exponents and combine everything into just one base. So now we would have the following. So we would have 1/2, then now I'll write this as the infinite sum. What was it? K is equal 0. We'll put this as 1 divided by 2 to the power k. Multiply this with the infinite sum yet again. This is for m is equal to 0 of 1 divided by 2 to the power m. Then we just multiply with our integral, 0 to 1. Then use the exponent rule, so u to the n, then u to the k, then u to the n, u to the k, and then u to the m. Add those up together for the exponent, so u to the power n plus k plus m, and then du. And then this is very simple to see that calculating this definite integral, so we're going to get the same thing. So I'll have 1/2, then I'm just basically just rewriting the same thing what we're given, or what was already written from before, 2 to the k, then the sum, m is equals 0, 1 divided by 2 to the power m, and so we just evaluate this definite integral, just use the power rule, so it's just u to the n plus k plus m plus 1, and then divide by that exponent, so n plus k plus m plus 1. Then this is going from between 0 to 1, but that's easy to see that plug 0, the whole term is going to vanish to 0, and you plug 1, so it's just 1 divided by that denominator you see. So now what we have is that for our a sub n integral that we just evaluated, is that it's just equal to 1/2 times the infinite sum, k is equal to 0, 1 divided by 2 to the power k, then same thing, m is equal to 0, 1 divided by 2 to the power m, and then just multiply this with, so it's 1, then divided by n plus k plus m plus 1. So now we go back to our given. So now this time we can actually write this as back to our limit originally. So the limit as n approaches infinity of n times a sub n. Then just basically just distribute the n to everything over here. So I'll put the n right there. So we have the limit n approaches infinity. So 1/2 infinite sum, k is equal to 0, 1 divided by 2 to the power k, multiplied by the infinite sum again. M is equal to 0 of 1 divided by 2 to the power m, then that's just multiplied by n, then divided by n plus k plus m plus 1, just like that. Okay, and then we can actually just take the limit of inside for n. None of these, the summation doesn't matter. There's nothing for m that's dependent on it. So really, we're just taking the limit of this piece. But obviously, you can either apply L'Hopital's rule. You can do that too. You get infinity over infinity in determinate form. Or you can also just divide n to both the top and bottom. So you're just left with 1. Then this will be 1 plus k divided by n plus m divided by n plus 1 divided by n. Take that limit. Everything from k, m plus 1. K plus m plus 1, that's all just going to be 0, so you're just left with 1 over 1, and so that limit itself is just equal to 1. So I'll just reiterate and say that, take this limit, this is just n approaches infinity, then that's just equal to 1. Okay, so just to reiterate that, so this just disappears. Then we're pretty much just almost done, because notice that indices does not matter here because they follow the same, well, I'm saying this in terms of notation since we have k and m, so you would think listing would be a little bit different, but if you actually just expand this out, there's actually just the same thing. It's double the, well, yeah, if you multiply the products together, it's, the exponent square. So really, in other words, I can say that the limit n approaches infinity of 1/2, then multiply by, so it's just the infinite sum, put this k is equal to 0, then 1 divided by 2 to the power k, we square that since it's just double. Then in other words, you can actually, again, this is still the geometric series, so we have the limit n approaches infinity, 1/2, and then multiply just by using that formula, so it'd be 1 then divided by 1 minus 1/2, then take that square, then, well, okay, there shouldn't be a limit since we already took that limit, and yeah, there shouldn't be a limit over here. So give me 1 second to rewrite everything. Okay, so everything's fixed. So now we would just have 1/2, then multiply by 1 divided by 1 minus 1/2. That's just equal to 2, and then square that. And so therefore we have 2 squared 4, then divided by 2, and so therefore the final answer is just 2, like so. And there we have it. Not as difficult than you'd think. Really, geometric series is a really powerful tool in using anything, especially when it comes to integrals. Especially once we get to this form right here, for example. So that's when it's really handy. In other words, so yeah, that's pretty cool if you ask me.